Did you get a notice?
I did not, but it's okay.
Oh, well, it's allegedly recording.
I also just started recording into the cloud, so maybe we'll have 2 recordings.
Oh, good job, Danny. See, I'm doing mine to my computer. You're doing it to the cloud.
Now we got it covered.
Hours combined, we will have a recording. Excellent. All right. What do you think? Should we start?
Yeah, should we start with the introductions of ourselves? So
Yeah, I think so. Hello. Welcome to the CMRR virtual tour. My name is Emily Allen, and I'm a research associate here at the University of Minnesota. I got my PhD here as well, so I've been here, and some undergrad as well. So I've been here a long time.
Daniel, you guys met me yesterday, or most of you met me yesterday. So I'm a PhD student in the same lab as Emily and Anu, and sort of loosely affiliated with CMR compared to the 2 of them. But
Okay, I'm Anahita Mehta. I'm also a research associate at in the same lab as Emily and Danny. And I just finished my first project at the CMRR, so I'm happy to tell you more about scanners, though Emily is definitely the most experienced here.
And
But-
I don't even officially
Yeah.
work at the CMRR. we all are in
Yeah.
Andrew Oxenham's auditory perception and cognition lab, but we like brain data, so that's why we're here.
great, so I'll kick it off. You've probably heard about the CMR several times now. It's the Center for Magnetic Resonance Research. And normally what we would do in a welcome weekend is sometime in the afternoon, everybody who's interested would come along on a walk through the 20 or 10 or 0 degree weather. And we would go over to the CMRR together and do an in-person tour, but we can't do that right now, obviously. So we're kind of showing you what that walk would look like. If you've ever looked at Google Maps at the campus, this should look familiar, but the kind of green, most of the green area right there in the middle is the east bank of the campus on the east side of the Mississippi River, which is running along the left side of the screen. And then the west bank is on the west side of the river, pretty self-explanatory. Elliott Hall's that little dot right there. And there's several ways to get to the CMR, but the way I think the way we usually take is kind of cutting through Dinkytown or going down University, which is sort of to the east. And the little red indicator line shows you one route. It's about a 20-minute walk, I think. I would guesstimate that's about right. About a mile, and it's behind the stadium. So there's several new constructions behind the stadium. That are other biomedical research facilities, and you can skip to the next slide, I think. So when you show up, this is what you'd see. It's a really pretty looking building, fairly new construction. The entrance is down there on the bottom right. It's kind of weird looking building. There's several other entrances researchers can use, but that's where your subjects might show up or where you'd come for the tour. And the CMR is really exciting because it houses very high field, high strength magnets. So the next slide is about what makes a magnet. So what is a Tesla? A Tesla, yes, is a Tesla, but not in this case. We're talking about the SI unit for magnetic field strength. So Teslas in the things that you may ever hear about might range from some magnetic fields on the strength of microteslas. So for example, the Earth's magnetic field is about 31.9 microteslas. A refrigerator magnet is measured in milliteslas usually, so we're talking about maybe 5 milliteslas. The strongest magnet in the whole universe that we can observe are magnetic fields coming from magnetar neutron stars, which is on the order of 10 to the 11 or 100 gigateslas. But somewhere right in the middle there, between the really small and the really large magnetic fields, we're talking about what you see in magnetic resonance imaging. So if you've ever been to a hospital and had like an MRI of your chest or leg or arm or whatever, or your brain, you were probably in a 1.5 Tesla magnet. So that's a standard kind of clinical use magnetic resonance imaging device. And it has a fairly strong but magnetic field, much stronger than what you see, for example, on the Earth's magnetic field. But for research purposes, and we'll talk about this, why this is in a second, you want stronger magnetic fields. So the CMRR specializes in high magnetic field resonance imaging. So our weakest research scanners start out around 3 Teslas, And then we also have two 7 Tesla scanners, and we also have the world's strongest magnet approved for human imaging at 10.5 Teslas. So this is really something you don't get anywhere else. And it's pretty much nearing the upper limit of what's feasible using modern technology. If you make the magnet smaller, you can get to even higher Tesla values, but of course you can't fit a person in it anymore, so it's only for small animal work. So for example, at 16 Teslas and above, magnetic fields are so strong that you can actually levitate small animals like frogs via diamagnetic levitation of the water that's in their entire body. So you can actually basically eliminate gravity for these animals and have them floating in space. And there are small magnets that are just like that at the CMR for research on small animals and other types of things. So why do we care about, oh yeah, this is a cool picture of a magnetar we saw. We just thought it looked cool, so we threw it in there. Why do we care about Teslas? Well, it might not get you to Mars, so you can send a Tesla out into space, but for us, we care about SNR, so signal to noise ratio. When you're doing imaging, the primary constraint on what you can do is basically how noisy is the data. There's just inherent thermal and other sources of noise in MRI data, and it corrupts your signal. And so you might want to image the brain, but you can't see it because it looks like a bunch of white noise. So at higher Teslas, you can get more signal in the same time, which you can kind of trade off. So we like SNR, but we also like resolution. So we can kind of trade our SNR bucks in for some resolution bucks. And we can start getting down to much lower resolutions than what would be feasible on, say, a typical medical scanner. So here are some images, for example, from a 7T. I believe these are the 7T images, right, Emily?
It might actually be 3T, but it's sub-millimeter resolution.
Okay. Yeah, so these are some high resolution anatomical images. This is a coronal slice of the brain. So think like a slice right through the head like this. So you can see the cortex ringing around the edge, and you can see subcortical structures in the middle. The left image and the right image are T1 and T2 weighted. These are two different types of anatomical images, and there are many other types of anatomical images you can collect to emphasize different structures in the brain. So you can infer brain structure from these images. Here's an example from one of my research projects that I mentioned yesterday. This is kind of a T1 weighted image zooming in on a subcortical structure called the pulvinar, and it's circled in the bottom panel there. So about on the order of a few centimeters long. So it's a really, really, really small structure. And using traditional imaging, like you would get in a hospital, you couldn't really resolve any substructure in this structure. But using 7T imaging, we can show, for example, here, these are retinotopic maps in the pulvinar. So we can actually show that two different locations in the brain that are only 1 millimeter apart, they prefer different, or they require more blood flow when you present stimuli in different locations in visual space. So if you present a stimulus at 3 o'clock, or you present a stimulus at noon, two different areas of the brain basically light up more for one or the other, just separated by 1 millimeter of space. And you can do this over the entire brain simultaneously using 7T imaging. So it's pretty cool.
Okay, so one really cool thing about MRI machines is that they are non-invasive. So you can get really good brain data and data from the whole body. I scan brains, so that's what I'm most accustomed to thinking about. But really, you can image the whole body without having to cut anyone open, insert anything into them, inject them with anything. So it's a very safe and humane way of doing research. But as with any superhero story, with great power comes great responsibility. Magnets are great resources, and we're very lucky to be able to use them, but there are important things to consider when working with strong magnets, like how ferromagnetic objects, or objects that can get magnetized, will behave in this magnetic field, which is why we have a rigorous screening process to make sure our subjects that we are scanning don't have any metal on them or in them. We make them change into scrubs before scanning them. We don't bring anything into the room where the magnet is that could cause damage to the scanner or be damaged by the scanner. For example, phones or credit cards can get damaged by these magnets. So if you walk into one of these rooms with your wallet, you might have a hard time using your credit card later. So this video is going to demonstrate how strong these magnetic fields are and why you need to be very careful when you're using these machines. So this is a video of a scanner that was being decommissioned, or like they were planning to, put it to bed. So they decided to have a little fun in a relatively safe and controlled way before doing that. So basically, they take several objects that are ferromagnetic and let them go near the magnet, which results in very intense projectiles. So do not try this at home. I also mentioned that this was not actually at the CMRR. I found this video online, but you'll see them play with the magnet, and then at some point they turn off the magnet by quenching it. So I'll explain what that means in a little bit.
Oh, he's almost got it. He's almost got it. Don't hurt yourself. Rob couldn't do this.
How many years has it been here?
Since 91, 92.
How long have you been here, Fred?
We're not talking about that.
Here we go. Haven't been a while.
We're going to have major healing coming out here. Major healing. Tack, though.
Yo, it's frozen. You can take a hammer to it.
Did I miss the party?
So as you could see, if a person were in the bore of the magnet, this is the bore, they would have been seriously injured or killed had you had some sort of projectile like the ones that they were throwing. Accidents like this can happen. For example, if you're in a clinical setting and your patient has an oxygen tank that you bring into the room, that tank would also quickly turn into a projectile and fly into the scanner with a lot of force that could actually kill someone. So it's scary to think about, but that's why we need to be very careful, and why the CMRR only allows people with access cards to open these rooms. And as you saw with the metal chair, it can be very hard to remove these objects once they go into the magnet. They just kind of stick there. There's so much force there that it's really hard to remove them. And the part where the guy was jokingly pulling the chair out, that was actually a bit of trickery. They had already quenched the magnet or killed it by the time the other guy was able to remove the chair. Okay, so MRI machines are superconducting, which means the coils in the magnets are cooled to cryogenic temperatures. So like below negative 180 degrees Celsius, which converts into negative 292 degrees Fahrenheit. So like super duper cold. And this removes electrical resistance and creates very strong magnetic fields. So when in this state, the magnets stay active at all times. You can't just flip a switch, turn them off when you're done using them. They remain active at all times. So it's extremely important to be mindful of the fact that when you're near an MRI machine, you are always in an active magnetic field, which can be dangerous if you aren't properly trained to work in such an environment. Now, let's say you do want to turn off your magnet. You need to do it right away. Say there's some sort of emergency, there's a person that's being pinned to the magnet by an object, it's a life or death situation. Then that's a situation when you would need to do something called quenching the magnet. So helium is what keeps a magnet in a superconductive state, and a quench is when that helium is quickly released from the MR machine causing it to no longer be superconductive and eliminating the magnetic field. So basically the magnet stops being a magnet. But quenching is something that you want to avoid as much as possible because helium is a very expensive resource. And actually, when I was starting my PhD, kind of early on, there was a helium shortage, and the CMRR was kind of panicking because if you don't have helium, you cannot do MRI work. Unfortunately, it ended up working out, but in addition to being a scarce resource, quenching can also damage the magnet, sometimes to the point where you might not be able to get it back up and running again. And ramping it up or, remagnetizing it takes a long time. So the picture you're seeing here is helium that's being vented out of the building and being released into the air after. So it's in a liquid state when it's keeping the magnet on, and then it gets released as vapor when it's being quenched. So an important thing is that this is being vented into the outside world. But if for some reason the venting does not work properly in the room and helium quickly fills the room, that could actually be lethal. So it's very important that if in a case of a quench, you get people out of that room as quickly as possible, just in case. But when people are trained properly and get good at using these magnets, cutting edge work can be done with these wonderful machines. And one great reason the University of Minnesota is so cool is that the CMRR is the most cutting edge neuroimaging facility in the world. People who work here, they're pioneers in the advancement of MRI technologies. They are the ones who developed the strongest magnets first in the world. There are MR physicists working on improving pulse sequences all the time. So we have some of the best pulse sequence development in the world, brilliant scientists that work here. And because of that, we're at the forefront of these imaging technologies. So if you're interested in this sort of imaging work, this is a really good place to be.
Okay, so just to prove what Emily said was correct in terms of it is the leading neuroimaging center in the world, is just this very extensive list of MR magnets that are available at the CMRR. So we have 3 3T scanners. For reference, most MR facilities at universities have 1 or 2. We have 1.5, 270 scanners, which is extremely rare. 1 10.5 Tesla scanner, 1 9.4 Tesla scanner, 1 16.4 Tesla that's currently being used for small animal scanning, and 1 17 Tesla vertical bore magnet for levitation. So as you can think about, this is beyond cutting edge, as a lot of people at the CMR say it's almost bleeding edge technology, because everything in the MR world usually has a lot of contributions from the CMRR. And the other imaging technologies available here are PET and CT. And the CMRR also has a cyclotron, which is like a smaller particle accelerator. So like a compact particle accelerator, which helps you to produce radioactive isotopes. So that can be used in different imaging procedures. Okay. So here's a quick video that will take you through a very quick virtual tour of the CMRR, just so you can get a flavor of how many different scanners are there. So Emily can play that.
The Center for Magnetic Resonance Research is home to some of the most advanced MR instrumentation in the world, including the world's first 10.5T clinical imaging magnet, complemented by research faculty and staff that provide unique expertise in imaging physics, engineering, and signal processing. Over 30 radiology department research faculty work at CMRR. Our trainees have opportunities to collaborate with CMRR faculty in high field strength MRI research.
All right, so that was just to show you what the different scanners look like. And here we have a map of the building that Danny had shown earlier, the inside map of it. And it's just highlighting where all these different scanners are located. And as you can see, are also these dashed lines indicating how far the magnetic field extends. So as now you can see from the yellow lines that even if you are not at the scanner or in the scanner room, there is always an active magnetic field around you. And the stronger the magnet, obviously. So for example, the 10.5 Tesla has a huge magnetic field that can be felt much beyond the room. And these are all actively shielded scanners. And so you can have your laptop or something in the console room, which we'll see later, but just be aware that you're in a very high magnetic field at all times. And just to give you a point of reference of where you would be, if you would be coming from the street, then the entrance would be somewhere here. You walk in, there's this really nice reception, and then there are a bunch of offices and a lot of scanners. And highlighted here is the magnet garden is for posterity when scanners are put to bed or have served their purpose. They are laid to rest in the magnet garden, and it's really cool to see these, not relics, but so the 70 scanner, the first 70 scanner in the world that Emily used extensively was finally laid to rest here. And it's really cool to see this technology. You're just surrounded by it, and it's really inspiring for science. All right.
Yeah, so in case you haven't gotten the gist yet, we're really, really proud of our 10.5T. We brag about it like every day. But these magnets are huge. So one thing we didn't really talk about is that in order to achieve a larger field strength, a higher field strength, you either need a much larger magnet or you need a smaller bore. But people only can get so small. So eventually you can't make the bore any smaller and you have to make the magnet larger. So the 10.5T is gigantic. It was built in Europe, shipped over to here through the Great Lakes via the Duluth Harbor. And then I can't remember if it was trucked or railroaded down here to Minneapolis.
I think it was a truck.
Okay. Yeah, I wasn't there at the time, so I just hear
So
these
I think
stories.
they actually had to shut down the blue line or something when they were moving it in. So I can't remember exactly.
Yeah, it was a big ordeal. And when they actually brought it to the CMRR, there was no way to get it in the building without deleting an entire wall, just removing an entire wall, sliding it in, and then rebuilding the wall around where it was. So I think there's a video of this process, yeah, of them actually getting the magnet in the facility.
This is a very ambitious project, faced with many scientific challenges. But the first challenge was to build such a magnet, and that challenge, in principle, has been met. I mean, this magnet was tested at 10.5 Tesla. This is going to be used for magnetic resonance imaging-based studies of the human body, predominantly brain, but also other parts of the body. And we expect with this magnetic field to reach the kind of detailed information we are unable to get with even the most advanced scanners we have in the world. The next challenge will be really on the CMRR scientists, and in fact to work out the technology and exploit what a 10.5 Tesla can potentially deliver. Many of the magnets in this building are first of their kind. They represent the state of the art. They are the most advanced scanners in the world. And this is now another phase of development, actually, to surpass the capabilities.
Yeah, so here's a picture of Camille, the director of the center. next to the magnet, and you can kind of get a sense of just how terrifyingly large this thing is. I think it said it was 110 tons. When you're sitting in one of these magnets, I've never been in the 10.5, but I have been in the 70. It's kind of crazy to realize you're in this little tube surrounded by just like a solid 2 or 3 feet of metal. It's quite an intense thing. And this guy really is the pioneer that led a lot of this work. He's one of the authors on the first papers to report the BOLD signal, the blood oxygenation level dependent signal. That is the fMRI signal we use for most of our work to infer neural activity from MRI signals. So he really is a big reason that this entire field of neuroimaging in vivo exists.
Okay, so after years of work getting the magnet one installed, which you saw was quite a process, removing an entire wall and shipping it across the sea in order to get it here, and then ramping it up, which takes a long time, getting it to the 10.5 Tesla magnetic strength, and doing a ton of testing and getting a lot of approval, FDA approval for everything. It's finally up and running after many years, and it is now approved for scanning humans. So it's very exciting. And you can just see the joy on these scientists' faces when they got their first human image at the 10.5 T. In this case, it was a human torso, but it was just so much work to get to this point that they were just absolutely gleeful when this day came. It was a big day. So while the 10.5 T is new and fancy and cool, it is still a work in progress. Scientists are still working on coming up with the best ways to acquire really, really good data there. And the 7Ts, on the other hand, which we've been using for a lot longer, we have a much better handle on in terms of getting really nice brain data. So this is the 7T-AS. So AS stands for active shielding, which Anu had mentioned, which essentially means the fringe fields are suppressed within the cryostat, within the magnet itself, rather than contained by like ferromagnetic materials that are outside the scanner and in the walls. So that's in contrast to passive shielding, which is indeed when you install iron beams or steel plates into the walls and the ceiling and the floor of the room in order to kind of suppress the magnetic field. Active shielding is much more effective than passive, but I think it's a lot more expensive too. They're both very expensive though. But now we basically have everything actively shielded. So the newest 7T to get installed in the last couple of years is the Terra, which is the first 7T ever to be approved for clinical use. So if you think of hospitals, standard medical MRI machines are usually around 1.5 Tesla. 3 Tesla is also approved for clinical use now, and 7T is the very new addition to this list. So this is also an exciting new thing at the CMRR. So that was the newest. And here's a picture of the first 7 Tesla ever. It was decommissioned at the end of 2019 after being in use for over 20 years. It was definitely an old school scanner, not as automated as the newer scanners are today. It could be very fickle at times, but a lot of groundbreaking research was done at this scanner. So we were pretty sad to see it go. So this is a couple of us giving it a final goodbye. This is after I had been using it pretty much every single day for a year. So it was my home away from home. So it was kind of sad to see it go away. And this scanner was one of the passively shielded ones. So because the magnetic field spread out further, that meant that even when you're in the console room, you can damage your phone and things like that. So it's better to be actively shielded.
Okay, so this is the magnet garden that I was referring to earlier from the map. And as you can see, the 7T is not totally gone, and it's now a work of art in our magnet garden, right next to the first 4T scanner. And yes, this is a typical snow day in Minnesota. But it's just a reminder of how far the automation has come in scanners. So the 3Ts are, so that's the scanner that I work on. And we have three 3T scanners, 3T A, B, and C. They're all actively shielded, and they are for clinical research, as well as two of them are primarily for non-clinical research. And they're really great scanners. You can get excellent, reliable data from them. And in terms of how small the resolution is, so obviously for 70, you can easily go sub-millimeter. But even here, even for a 3T regular almost whole brain scan, if you use something like a 2 millimeter voxel, that is still a very good resolution. So you have each voxel is 2 by 2 by 2 millimeters. And this amount of resolution is way better than anything you can get with any other imaging techniques. So even at the 3Ts, you can really get some excellent insight into brain data. And just to show you how big a deal CMRR is, Amy Klobuchar, who is the senator in Minnesota, visited to discuss the brain research here through advancing innovative neurotechnologies. And that's the BRAIN initiative during the Obama administration, and a research effort to map the human brain in hopes of finding new ways to prevent and cure brain disorders such as Alzheimer's, autism, epilepsy. And all of this research currently does go on at the CMRR. The CMRR is not only a research institute, there's a lot of clinical and clinic adjacent research that gets done. So here you can see her with Camille and at the 3T. And as we said, this is a photo of Emily in the 3TB console room. So we've shown you a lot of pictures of magnets, but if you do MRI research, you'll probably be on the other side of the magnet, so in the console room. So here we have all the stimulus computers, all the data acquisition computers in this room, and obviously none of it can be in the magnet room because they will get pulled towards the magnet. And sorry, you can also talk to the participants through this room. So the magnets are very loud if you've ever been in a MR scanner. And so they usually have hearing protection and headphones, so you can communicate with the participants from the console room. Right.
So one really cool and unique part of the CMRR is that rather than relying on external resources for all of the hardware and fabrication needs, the CMRR can actually do a lot of its own fabrication on site. So there is an electronics lab, a fabrication lab, a machine shop. So one of the example advantages of this is that certain projects might need different types of radio frequency coils to maximize, say, signal gain in a certain area of the brain, or to meet certain design restrictions for an experiment. And normally you would need to go contact a manufacturer and submit a proposal and get quotes and do all this stuff. Here we can sort of just make our own RF coils, and we can make our own apparatuses to realize whatever type of experiment you want to do at the CMRR. And you can learn how to use all these tools if you're interested in that sort of thing. Even if you're a psychology student, you don't have to be an engineering or a radiology student to gain access and learn how to use these tools. And one of the funny memories I have of my tour of the CMRR is before they moved everything around and did some construction, the machine shop actually used to be part in one of the magnetic fields. So you could, like, as you were working on a machine shop problem, you could feel your tools actually be pulled towards the magnet. And so one wall was almost like quasi-magnetized. And you could like leave a hammer or like a knife or something and have it almost float in the air. It was kind of a little risky, but they've since upgraded the facility and no longer is a machine shop magnetized.
They called it the world's most dangerous machine shop.
Lovingly.
Lovingly.
So you can jump to the next slide. We have a seminar room, not much to be said about that. Other than that, this monthly seminars are pretty cool and they're open to everybody. So at a regular university, you might get one seminar a year on any sort of imaging topic of inequality. But here we have so many people working on imaging that you can literally go to a fantastic talk like on a monthly or weekly basis about imaging. And also, I think this is all done now, but there was new construction to upgrade the CMR going on last year. I think it's all finished now. So they've rearranged, gotten rid of some old magnets, upgraded to new magnets, added more office spaces, enhanced the courtyard, added a cool, like magical tunnel that crosses through the courtyard so you can get from one side of the building to the other faster. You used to have to kind of go all the way around the building if you wanted to get from one side to the other. And now there's like a little shortcut tunnel that I have yet to see, but it's exciting. And in general, it goes to show that the university is super invested in the center, and so is the state of Minnesota. It's a really kind of a shining, what's the word, crowning jewel of the university campus. And we also have a lot of compute resources. If you're going to do imaging, you are going to have a lot of data. Data for MRI is gigantic. So there's hundreds of servers at the CMR. Many of them are just dedicated to individual scanners to say, take the data that comes off the scanner in a raw format and convert it into images. So the data that's coming from each individual RF coil is not a picture. It's a radio frequency signal that has to be converted into a 3D image. And so that's, some of the servers are for that. Some of the servers are just for analysis. And across all these servers, there's thousands of computer cores and terabytes of memory to work with. So here's an example of one of the servers that I see. The different numbers here indicate the activity on the different computer cores on the server that I access to do my analyses. And it's pretty cool to be sitting there and analyzing data that's hundreds of gigabytes in size. A normal computer couldn't even load the data set, much less process it. But on these servers, you can manipulate thousands of images simultaneously and do all kinds of cool analyses.
So as we mentioned, cool work happens at the CMRR. Maybe some of you have heard of the Human Connectome project. It was this huge undertaking that the CMRR has been involved in. A massive amount of 3T and 7T data and other imaging data has been collected across, I think, around 20 different studies across multiple age groups at this point, in a sort of systematic effort to map macroscopic human brain circuits and their relationship to behavior in a really large population of humans. And the data is publicly available for others to explore and analyze, which is really cool. So if you do want to learn more about that, you can go to humanconnectome.org. And while the Human Connectome focused on getting data from a huge number of people, there's also a newly published natural scenes data set, which is an example of what we might call a deep data set, where the focus was on getting a huge amount of brain data from a smaller number of subjects. In this case, it was 8 subjects, as they viewed and performed a behavioral task on a really large stimulus set full of natural scenes. And this is the project that I was involved in at the 7T, the one that got decommissioned for a year straight. It was a huge undertaking. And just to show you, just demonstrate that a little bit, just a fraction of that. This is a carpet plot that shows kind of a small bit of the scale of this project, just showing that each tiny dot is a brain response for 1 voxel in a subject's visual cortex to a single trial or a single image. And we have whole brain data for each subject, so it's millions of data points per subject. So the whole data set is many terabytes large. We ended up buying a whole server just for this study, and we acquired a lot of different types of imaging data. And this GIF on the right is showing 2 types of structural data, a T1 and T2, and then a functional image, which is an EPI. And so this is showing 3 different views of a brain for one subject. So you've got axial, coronal, and sagittal. So this is one subject. This is another subject. So for all 8 of the subjects. So it's all really high quality data, which was really cool. We had each subject coming in to be scanned about once a week over the course of a year. And we were so lucky to have such amazing subjects that were willing to come back so many times and give us such great data. So to get really good data, you have to have subjects that are, kind of statuesque. They just do not move while you're scanning them, because motion is very hard to correct for. They stay alert, they stay awake, which is also very hard to do because you're basically laying in a bed in a nice, dark, warm environment. And you have to stay alert and actually perform the task. So it's not easy. And so treat your subjects well because they are very valuable. Without them, we wouldn't have this data set. So we're really excited about the end result. And the entire data set is available to the public now. And if you want to learn more about that, you can go to naturalscenesdataset.org. And so that's just, a tiny fraction of the work that's being done at the CMRR. If you go to the website, www.cmrr.umn.edu, and I say www because if you don't put the 3 W's, the website no longer works. I don't know if you guys have noticed this, but Anu and Danny, no. But yeah, it doesn't work unless you have that there, which I don't know what happened. It's in the last couple of months. Anyway, so you can go to that website and you can click on this research tab up here just to see kind of some of the diversity of projects that are being worked on. And so, there's things like engineering work that Danny had kind of mentioned on developing new coils to improve imaging data quality. Alex Bratch, who helped us give this tour last year, he recently got his PhD from the psych department, and he's doing this type of work in his postdoc. He's actually doing a postdoc at Stanford, but physically is still here at the CMRR because this is the best place to be to do this type of research. There's vascular imaging work, which is imaging of veins and arteries. You can get really cool images of like angiograms is what they're called, without having to inject any sort of contrast agents or anything. Like you get these really cool pictures of the veins and the arteries. There's dental imaging going on, which I didn't even know about, but it's a way to actually look inside people's teeth. Very cool. Breast and prostate cancer research, exploring the effects of diabetes on brain structure and function, schizophrenia work. Anu and I do auditory fMRI research, so understanding how humans process sound in auditory cortex, which, as Anu mentioned, is tricky because MRI machines are very noisy. Like a pulse sequence could sound like really loud. So that's why hearing protection is just critical. But it also makes it kind of tricky to do auditory research where you're also like presenting sounds that you want people to be listening to over this loud scanner noise. So there's many different avenues that can be explored with this non-invasive imaging. And so the CMRR is a really, really great resource to have. And I'm not saying it's easy research. It's not at all easy. The projects can take years, but it is really fascinating work, I think.
Okay. And given that in addition to the MRI data being so computationally expensive and the data sets being so massive, it's also expensive to acquire MR data. So it is important to have a good chunk of grant funding. And it is also very expensive if you mess up and you have to do the experiment again. So the moral of the story and the only advice you should be listening to is pilot your study properly and design the experiment carefully, because as you can see on the slide, these are the hourly rates. So for example, each experiment that Emily and I run is a 2-hour experiment. And we don't use an MR technician. So if you can think about it, it's almost $1,000, including participant payments for one participant's data. So don't take this research lightly, I would say, but the results can be fascinating. You can get some incredible insights into how like sensory mechanisms work. And the CMRR also has a host of services like MR technicians who have an hourly rate. At the CMRR, you have the option of having a tech or not. So that's what makes the scanning actually less expensive. So these rates, believe it or not, are actually much cheaper than rates across the US. And we also have on-site MR engineers, technicians, technologists help with making pulse sequences. So yeah, it's definitely the place to be if you're interested in MRI research.
And to tack on to that, I was just going to mention that if you notice something when you're scanning someone and it looks a little concerning, and you yourself are not, an expert, you're not a medical doctor or anything, you can actually send the image to a radiologist, and they will let you know if there's something concerning for that participant that they should go to a doctor to seek treatment or something, or get looked at. Because it's not our job as researchers to be diagnosing these things, but it's nice to have a radiologist who can help you with that sort of thing.
Yep. And lastly, for some fun memes related to MR, sorry for all the Nickelback fans in the house, but and if you have any questions regarding the facilities or the technology, please ask any questions you may have.
Yeah.
Or if anybody is interested, and it would be nice to know if anybody is even interested in MR.
Yeah,
research.
after this presentation, would you be into doing this type of research, or would you run away as fast as possible?
So are all of y'all, I assume, psych students? I mean, prospective psych students. That's cool.
And what labs are you thinking about?
I got accepted into Dr. Lee's lab.
Oh, very cool.
Very cool.
She's great.
Yeah, we love Vanessa. She's like
Mhm.
a superhero.
Yeah, she really is.
And I'm sorry, I've been accepted with Paul Shorter.
Oh, Paul, did you say Paul Schrader?
Yeah.
Oh, very cool. Yeah. He does really cool work. Excellent.
Yeah, so I'm amazing to Dr. Pilares.
Oh.
Yeah.
Oh, yep. Mhm.
Yeah, that's fascinating work. And she's currently in this whole pandemic and trust research is really fascinating. Yeah, really
Mhm.
cool.